The proof of the optimality of Huffman codes depends on the existence of optimal codes. In other words, in order to show that Huffman codes are optimal, you first have to show that there exists at least one optimal code. Now, most treatments of Huffman coding, at least every treatment that I've seen, when they prove that Huffman coding is optimal, they just assume that this is true. They assume that there exists at least one optimal code. But this is not completely obvious. It's not that trivial to actually write down a proof of this fact. So in this video, I'd like to go through a fairly detailed proof of this. You know, I'm sure that someone has proven it all out there already, but at least I'm not aware of it. So let's go through that in some detail. So what are we going to prove? So we are going to prove the following. This was a lemma in our leading up to the proof of the optimality of Huffman codes on the existence of an optimal code. And so what are we claiming here? We're claiming that if x is a finite source alphabet, x is finite, and p is a PMF on x, then there exists an optimal code. There exists an optimal code for p. Optimal code for p. In other words, what do I mean by optimal code? Of course, I just mean a uniquely decodable code. And in fact, there is a prefix code by this, by the Kraft-Macmillan theorem, a uniquely decodable code with minimal expected code word length. Minimal L, which is the sum of the lengths times the probabilities, lengths of the code words. So this is what we're going to prove. Now, before we dive into the proof, let me make a little remark to explain why this is not completely trivial. So this is just going to be a little informal discussion. So suppose that this were not true. So suppose not, then so that would mean that if we had some code C1, actually let me put superscript C1, that there would be some other code C2 that had strictly better expected code word length, right? Because otherwise C1 would be optimal. So that would mean that, so if not, that implies that given C1, we get some C2 that's strictly better, and then so forth. You know, then likewise, given C2, there's some C3 that's even better than that, and for C3, there's another one that's better. So we get this infinite sequence of codes that would imply that there is this infinite sequence with strictly decreasing expected code word lengths. Now, each of these codes is distinct. They must be different codes because they have different expected code word lengths. And if you think about it for a minute, this implies that there's some I for which the length I is the length of the ith code word is getting bigger and bigger. It's getting arbitrarily large. So if I put the superscript n to denote the length of the ith code word for the nth code, the supremum over n here, the sup of this is infinity. These are getting arbitrarily large. Not necessarily converging to infinity. It could drop back down every once in a while, but these are getting arbitrarily large. And now this is a bit funny because these lengths are decreasing, right? And yet this little length of this code word is getting big. So if it were the case that pi, the corresponding probability, were positive, then there would be a contradiction here, right? Because that would imply that, you know, the length here, n, which is, so the sup over these lengths, which is, of course, just the sum of the lengths for the nth code times their probabilities, that this is infinity. Because the pi, you know, well, I should put like j here or something. J. That for the jth term in this sum, that term is getting arbitrarily large, and because pj is positive. So that would be a contradiction because this first one was finite, and yet this sequence is like getting arbitrarily large, but that's a contradiction. Okay, so that would certainly be a contradiction, but that leads us to, or that indicates sort of the subtlety in proving this, which is that some of these p's could be 0. Some of these could be 0. So, but what if pj is 0? Then what? Now you might say, oh well, if pj is 0, that means that the probability of that source symbol occurring is 0. So we can just ignore those. We don't even need to worry about those. But you can't really just ignore them, because you still need to have a uniquely decodable code. You might say, oh, okay, we'll just focus on the p's that are positive and then define a uniquely decodable code over those, and then pick any old code words for the others. But you're not guaranteed that you can always pick any old code words for the others and still have a uniquely decodable code. So that's the subtlety. Now you might say, oh well, but those source symbols never happen. So as a practical matter, it's for all intents and purposes, it's uniquely decodable, with probability 1 or something like that, because for any given sequence of source symbols that can occur with some positive probability, we can always uniquely decode it in a unique way. And that's fair enough. That's true. But this is true more generally, even if some of the p's are 0. So let's go ahead and prove that. So if all the p's were positive, then this little remark here would show the result. But let's allow for the possibility that some of the p's are 0, and let's prove it in that less trivial case. All right, so here is the proof. So let's since our source alphabet is finite, let's go ahead and just define its size to be n. We're going to be using this number n. And we have our p's, so we're given our x and we're given our p. It's PMF on x. So let's number those p's. Let's say p is p1 up to pn. And let's suppose we may as well order these. If we labeled the elements of x as x1 up to xn, and pi was the probability corresponding to xi, then we can always label these in such a way that the p's are non-decreasing. So we may as well assume. So let's say it this way. We may as well label these in such a way, or well, let's say label these in such a way that P1 is greater or equal to P2, greater or equal to Pk, and let's say that k is such that it's this is the last positive one, and after this, all of them are 0. So Pk plus 1 up to Pn are all 0. All right. Now, let's construct a certain code on this set. It's going to be a sort of a code that will be useful for us sort of as a reference. So we can trivially construct a uniquely decodable code for this with expected code word length less or equal to n. So here's how we can do that. So let's define code cn by the following. Let's say cn of, so we need a code word for each of these x's. So let's define x1 as 0. It's going to be a binary code. We're going to do a binary code. 1 0 cn x3 1 1 0 and so forth. Just 1 1 1 blah blah blah. Just a bunch of ones and then a 0. So then the last one, xn, is going to be how many ones? It'll be n minus 1 ones, n minus 1 ones, and then a 0. So this is certainly actually it's a prefix code, so it's certainly uniquely decodable, and all of the code words have length less or equal to n, because this last one had length n. In general, the ith one has length I. So we know from this that the expected code word length of this code, let's denote that L sub Cn is less or equal to n, because, L, well, I can just put it this way. The length of the ith code word is I, which is less or equal to n. So yeah, so that implies blah, 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 since, go ahead and write it out, since this is true. Okay, very good. So now let's define some numbers. So we're going to define some certain bounds associated with these p's and with this n. So let's define some numbers. So we defined our c, and now let's define, unrelated to c, for I equals 1 up to k, for the, remember that k was the last positive p. For these i's, let's let m sub I equal n over pi. Now, why did I define this? The reason why is because, so this implies with these m's, that means that, so if Li is greater or equal to Mi, then Li pi is greater or equal to n. Because Mi, so if Li is greater or equal to Mi, which is n over pi, just move the pi over, and you get Li pi is greater or equal to n. So the reason why I defined these is because if you had a code with where the ith code word had length Li and that was greater than Mi, then immediately you'll be able to conclude that the expected code word length is greater or equal to this, which is greater or equal to n, which is greater or equal to this. So these are sort of upper bounds on the lengths of codes that are going to be, if they're worse than this, if they're longer than this, then your code is going to be worse than our sort of reference code here. All right, so now, we're making a bunch of definitions. Let's define some other stuff. So let's let script C. This is going to be a collection of codes, a set of codes. So it's going to be the set of codes C such that C is uniquely decodable, and let's say C is uniquely decodable with lengths L1 up to Ln, where Li is less or equal to Mi for I from 1 to k. For I, not for all I, just for the indices with positive probabilities. Right? Because, well, those are the only i's for which we've defined Mi. So we're going to consider all the codes with sort of reasonable lengths, lengths that are no worse than this sort of bound Mi. And now, note, so we can note right off the bat that our Cn is in this set. And why is that? So it's Cn, I claim that Cn, this reference code, is in this collection of codes. Since Li, we know that the length of the ith code word is always less or equal to n, right? That was our Li, whatever. The Li for this n code. I don't know, what should I call that? LICN or something like that. Okay, so the length of the ith code word for this code is less or equal to n, and n is just pi times mi pi, which is certainly less or equal to mi, since pi is a probability. So then we know that the lengths of this code are less or equal to mi, and it's uniquely decodable, so that therefore it's in this set. All right. That's, of course, for all I from 1 to k. Now, let's think about the set of expected code word lengths corresponding to these codes here. So let's define the following. So let's let script L be the collection, or the set of the numbers, the real numbers. So these are, I could put it this way. These are numbers that are the expected code word lengths of well, I'll just put it this way. It's the expected code word length of C as C ranges over all the codes in our set script C. So we just get all those numbers. And now, so note that this set of all codes is potentially infinitely large. It's going to be infinitely large, even though the first k code words are all have their lengths bounded. If there are some p's that are 0, so if there's some of these here, if k is not n, if there's some 0 p's, then the length of the code words for some of those guys can be getting arbitrarily long. So you can have there can be those lengths can be sort of going to infinity. They can be getting arbitrarily large. So this set could be potentially infinite, but this set, this L, is going to be a finite set. And why is that? Because so we know that that the set of possible lengths for I from 1 to k of codes in this set are all that's a finite set. You know, the number of possible sets of lengths is going to be bounded by m1 times m2 up to mk. The sets of lengths for I from 1 to k. And since pi is 0 for all the others, k plus 1 up to n, then in fact any code with the same lengths for I from 1 to k, any code that has any two codes that have the same code word lengths for I from 1 to k is going to have the same L. So even though there's sort of infinitely many, then there's only going to be finitely many lengths. So maybe let me write down why that's the case. So L is finite since the expected code word length of a code C is the same as for another code, as long as if Li is the same as Li prime, where Li is the code word length of the ith code word for this C, and this is corresponding thing for C prime for I from 1 to k. It doesn't matter what they are afterwards. And we know that each of these lengths is bounded by the corresponding mi. Okay, so L is finite. And now what can we conclude from this? Well, we know that there's some minimal element of L. Right? So therefore, L has a minimal element as long as it's non-empty, and we know that it's non-empty since Cn is in C, and so so LCn is in L. So we know that L is non-empty, and so we can let non-empty and finite. So we can let's say C star be one of these codes, well, one of these here, that has minimal expected code word length, where it's minimal over L, such that L, the expected code word length of C star, equals the min of all these numbers in L. All right, so now this is looking like a good candidate for an optimal code. So let's check. So this is so is this optimal? So we'd like to say that this is optimal. And so let's check. So let's let C be any old uniquely decodable code, and let's see, is its expected code word length bigger or equal to this LC star? Well, so there's two possibilities. Either it's in our set script C or it's not. So if it's in script C, then we know that its expected code word length was one of these numbers right here, but LC star was minimal over all those. So that would immediately imply that L C star is less or equal to LC. So that handles that case, and on the other hand, let's suppose that it's not. So let me do that in a different color. If C is not in C script C, then what? Well, what was the definition of our script C here? So it's uniquely decodable, and has these lengths are bounded. So this was the key thing here. The lengths were bounded by mi. So if we have some uniquely decodable code that is not in this set, then that means that for some j, the length must be greater than mi. So if this, then let's say Lj is greater than Mj for some j. And that's a j from 1 to k. So what does this imply? Well, we were talking about earlier. We said, oh, well, if it was greater, then we're going to know that it's going to have greater expected code word length than this guy. So let's write down why that is. So this would imply that the expected code word length of this guy, which is the sum over his lengths times the probabilities, is certainly greater or equal to the length times the probability of just the jth one. And this length is greater than mj, and pj is positive, so, or is non-negative, so oh, well, let's see. Yeah, pj is positive, so this is a strict inequality. We wouldn't need it to be strict, but it is in fact strict since j is between 1 and k. And so then what can we conclude? mj pj, what is that? mj pj is just equal to n by our definition of mj. So this equals n. And n, we know, is greater or equal to the expected code word of length of this reference code. So that's where our reference code, another place that our reference code comes into play. And our reference code, remember, is in this set C. So its expected code word length is in this set L. And so therefore the length of our optimal, or our hopefully optimal code, is at least as good as the length of this Cn of our reference code. So that implies that this length is greater or equal to LC star, since Cn is in C. And that's just what we wanted to prove, right? So that implies that the expected code word length of this guy is always greater or equal to the other one, the optimal, the supposedly, hopefully optimal one. So now we know that indeed it is optimal, because this was some arbitrary, uniquely decodable code. So we conclude that C star is optimal, and so therefore there exists an optimal code.